All right, so our next topic is going to be redox reactions, also called oxidation reduction reactions. Pretty much what we're doing when we talk about redox reactions is we are tracking the movement of electrons. What I mean by this is we might want to look at maybe like an iron atom, and we want to see, oh, if I react it with this other compound, at the end of the reaction, did that iron atom end up with more electrons or less electrons? In order to do that, we have to determine its oxidation state. When we talk about oxidation state, it's like this hypothetical charge that that atom would have in that reaction in order to get a full shell. So you can almost think about it like we're doing the ionic charges that we talked about earlier, where if you gain electrons or lose electrons, we're going to get those positive or negative charges from like the cations and anions. So that's a way you can think about it. So a couple rules to determine oxidation states. Our first rule is for a single type of atom, that oxidation state is going to be 0. It'll be neutral. So a couple different ways that you might see this. First way is if you have like a single atom by itself. So if you have any metals, so maybe like copper metal, it'll be by itself, so it'll be neutral, no charge. Another thing you might see is something like a noble gas. So maybe something like helium. Again, not bonded to anything, so neutral, no charge. A third way you might see this is for diatomic molecules. So let's say we have something like chlorine, Cl2, chlorine gas. So Cl2, there are 2 chlorines there because of that little number 2, but it's a single type of atom. It's just chlorine. So it's still going to have no charge. And the reason for that is there's no difference in electronegativity. So no difference in electronegativity. It's not going to have, or there's not going to be like one chlorine that's like more negative or more positive in that sharing of electrons. So overall oxidation state of 0. Second situation we might have is that the when we add up all of the oxidation states, so the sum of our oxidation states has to equal the its initial charge. So like sum of oxidation states for neutral compound is 0. And we'll talk about that rule a little bit more when we come back and we do an actual example. But our next rule is the sum of oxidation states for a polyatomic ion is its charge. So I don't think we have an example for that. So like for example, if we have something like NH4 plus, when I do the oxidation states for each of those, I'll say, oh, each hydrogen is going to be, well, actually, let's do the next rule and then we'll come back to this. And we'll kind of do that as an example together. But our next rule is that the most electronegative atom will be negative. And the least electronegative atom will be positive in a compound. And then our last rule is that some atoms will always have same oxidation state. So for example, let's make a little bit of room here. So for example, some of them are going to be your group 1 metals. Group 1 metals are always going to be positive 1 because those are always going to want to lose 1 electron in a reaction. So like group 1, column 1, that's what I mean for that. Group 2, will always be positive 2. And then your fluorine is always going to be negative 1. This just has to do with electronegativity. So for the most part, your metals in group 1 and group 2, or always your metals in group 1 and group 2, these are going to be your least electronegative. And then fluorine, no matter what it's connected to, it's going to be the most electronegative. So you always know what those charges are going to be. And then number 6 is going to be for most of the time there's going to be certain oxidation numbers for oxygen, hydrogen, and chlorine. So for most of the time, for oxygen will have an oxidation state of -2 because it wants 2 more electrons when it bonds. Only exception is when you have peroxides, so something like H2O2. Then oxygen's oxidation number will be -1 instead. The next one is going to be for hydrogen. Hydrogen is usually going to be +1. And it's usually going to be +1 because it's going to usually be the least electronegative atom. So this is normally going to be when it's with nonmetals. Our exception here is going to be if it's with a metal, then it's going to be less electronegative. If it's with the metal, it's going to be more electronegative, so it'll be -1. So with the metal. And then our last one is going to be for chlorine. Chlorine is usually going to be -1. It's usually going to be more electronegative than anything it's with. This is going to be with the exception if it's with oxygen or fluorine, in which case those are going to be more electronegative, and those are going to kind of take priority when it comes to figuring out which atom is going to be negative in your bond. So those are our oxidation state rules. It looks like a lot of rules, but once we start doing examples, you'll see it's a lot more straightforward. So let's do this example that I talked about earlier. So I'll do it over here. NH4+. So our rule was that whatever's more electronegative is going to be our negative atom. So I know nitrogen is going to be negative. And then our hydrogen, it's bonded with a nonmetal. So now that one's going to be our positive atom. And then overall, when we're done, we have to have a positive charge. So I have no rules for nitrogen, but I do have rules for hydrogen. I know that hydrogen is going to have a positive 1 charge. So at positive 1, well, oxidation state, so the positive number first. Well, overall, if each hydrogen has a positive 1 charge, and there's 4 of them, then hydrogen should be giving me a positive 4 charge in total. So I can put like a positive 4. That's the overall contribution for hydrogen. Well, my nitrogen, on the other hand, it's going to have those 5 valence electrons, right? So now I need to figure out how many electrons is nitrogen kind of getting from this steel when it bonds with this hydrogen. Well, I know I need to end with a positive 1 charge. Well, if I already have positive 4, then I'm just going to say nitrogen is going to be negative 3. We need to flip those numbers. Hydrogen was 4 plus. I need to end up with 1 plus. So I'm going to do 3 minus. So when I combine these two numbers, negative 3, positive 4, gives me 1 positive. And that's what I want to end up with. So I would say my oxidation state for nitrogen is 3 minus. My oxidation state for hydrogen is 1 plus. And that gives me that overall charge of 1. So that's what's going to happen for polyatomic ions. When I add everything up, it'll have whatever charge it should have. When we talk about neutral atoms, for neutral compounds, if I have something like CO2, well, there is no charge here. So when I add up carbon and oxygen's oxidation states, should have no charge. Well, oxygen, I know has 6 valence electrons. We talked about the rule for oxygen that because it's the most electronegative, that's going to be the negative one. Oxygen is usually negative 2. So if oxygen got 2 more electrons, then it'd be negative 2. Well, there are 2 in total. So my total contribution for oxygen is going to be negative 4. So right off the bat, I know carbon, in order to make a neutral charge, a no charge, that carbon has to be 4 plus for its oxidation state. Right, and that makes sense. Carbon has 4 valence electrons. How many more does it need to get full? Well, it's going to need 4 more. And that's where that gaining 4 is going to come from. But positive 4, negative 4 gives me 0. And that's what I meant by that rule of neutral compounds. It's going to have no charge. So let's do an example. I want to track the electrons for this reaction, and I want to figure out how they're moving. So if I do this, I want to do the oxidation states for each of these atoms. Let's start over here with Fe2O3. Well, for the oxygen part, I know oxygen has an oxidation state of negative 2. There are 3 of those. So oxygen has a total oxidation state of negative 6. Well, iron has to have a total oxidation state of positive 6, but there's 2 of them. So each one has to have a positive 3. So this is going to be how you figure out the oxidation states for most of your atoms. You're going to take a look at your most electronegative one. Based on that, you have that rule where you already know what that oxidation state should be. And then from that, you're going to work backwards to figure out what your positive side needs to be. So oxidation state for iron, positive 3. Oxidation state for oxygen, 2 minus. Let's move on to this oxygen. Well, again, our rule, oxygen has to be negative 2. So overall contribution of negative 2. Well, in order for this carbon to have that same contribution in the opposite direction, so positive 2, this carbon has to be 2 plus. Okay, my iron, well, we already talked about that rule where if it's by itself, that oxidation state has to be 0. And then finally, CO2, well, each oxygen we said was -2. I have a total of 2 of those, so total contribution of 4 minus. So if carbon is going to have total contribution of 4 plus, each carbon here has to be 4 plus. So that's how I would find the oxidation states for each one. Now I kind of want to take a quick detour, and I want to track how those electrons are moving. So I want to start off with iron really quick. After it reacts, I see that iron goes from an oxidation state of +3 to an oxidation state of 0, which is kind of interesting, right? Seeing electrons changing like that. We're gaining electrons here in this reaction. So we're going to do something called half reactions. We're basically just going to break our redox reactions into 2 parts. So I want to talk about the reduction part of oxidation reduction. When we talk about reductions, we're talking about reactions where an atom or element is gaining electrons. So reduction is gaining electrons. You can think about it like you're reducing the negative charge. Or I mean, you're reducing the charge there. So let's focus on this iron part. For iron, we had Fe3 plus, we had our reaction arrow, and then we had Fe there with 0 charge. Well, how did we get there? In order for that reaction to have worked, our iron, our Fe, had to gain 3 electrons. So that's going to be like the half reaction for this particular redox reaction, where our iron is being reduced. Next, let's talk about this carbon atom. So for this carbon atom, we start over here with a +2 charge. We end over here with a +4 charge. So over here, now it looks like we're losing that negative charge. We're getting more and more positive. So this is the part where we call oxidation. When we talk about oxidation, we're looking at the element that is going to be losing electrons or getting more positive. So following that, our carbon atom started with a +2 charge on the reactant side. Then we ended off with a +4 on the product side. And I want to kind of figure out what happened with the electrons here. Well, in order to make these 2 sides equal to each other, +2 charge over here, +4 charge over here, I need to make my product side less positive to kind of match that +2 charge. So I'm going to add 2 electrons. If I do that, +4 plus -2 gives me +2. So that's how I'd write the half reaction for this oxidation half. So notice that for reduction, the electrons are going to be on the reactant side because that's the thing gaining electrons. So gaining electrons on the reactant side. For the oxidation half, we're losing electrons. If we're losing electrons, I want to separate them. So when we separate them, they're going to be on the product side. Just a little note here that for the oxidation half, this carbon atom even though it is losing electrons, it's being oxidized. Whatever is being oxidized, we can call that the reducing agent. All that means is it allows reduction to happen. Like an agent is something that like participates in something, so it's the thing that's participating or allowing reduction to happen. So the oxidation part is the reducing agent, facilitates reduction. I can do the same thing for the opposite side. Whatever is being reduced is facilitating oxidation. So iron here is our oxidizing agent. It's allowing oxidation to happen. So that's why we say that metals get oxidized when they rust. Metals undergoing that metals are our oxidation agent, but they're being reduced in their charge. So those are going to be redox reactions. So quick recap, single types of atoms always have neutral charge. When you sum up the oxidation states, it's always going to have the original charge of that compound. Neutral compounds mean the sum will be 0. Polyatomic ions mean it's going to match that charge. Most electronegative atom is always going to be the negative in the compound. So when we try to figure out oxidation numbers, that's where we're going to start. We look at the most electronegative atom. In general, there are a couple groups that are always going to be the same. Group 1 metals, anything in column 1 of the periodic table, always going to be positive 1. Group 2, those are always going to be positive 2. We know those because those are going to be our ionic bonds. Anything those are bonded to, those are going to end up as the least electronegative atom in that pair. I should probably add 4 ionic bonds. Our fluorine, always going to be -1 because it's always going to be your most electronegative atom on the periodic table. So when we figure out oxidation states, those are the ones we look for first. Do you see a group 1 metal? Do you see a group 2 metal? Do you see fluorine? If you don't see any of those three, then we go to this next category where most of the time these are really electronegative. So it's going to give us a good idea that it's usually going to have its charge. Oxygen, usually going to be -2. The only exception is if it's in a peroxide, in which case it's going to be -1. Hydrogen, it's going to be +1 if it's bonded with any non-metals, which will be most of the time. Only exception is if it's with a metal, it'll be -1. Chlorine, usually going to be -1, except if you're with something that's more electronegative. So unless you're with oxygen or fluorine. So that's redox reactions. I will leave you with an example I want you to practice with, and that's going to be on the reading quiz. So I want you to figure out your oxidation states for peroxide breaking down into water and oxygen gas. So I want you to practice that. I will give you a little hint. This is a special type of redox reaction. We call this disproportionate redox because the same element is being oxidized and reduced. Actually, you know what? The video is not too long. Okay, let's do this one together too. So let's explain what I'm talking about, where the same element is being both oxidized and reduced. So starting off with this first oxygen atom. Well, each oxygen I know has an oxidation state of -2, but there are 2 of those. So total contribution is going to be -4. Hydrogen, we know it's going to contribute an oxidation state of +1, but there are 2 of them, so it's going to be 2 plus, right? Well, that doesn't really work because our charges aren't balanced. So this is where we talked about that rule over here, where if oxygen is in a peroxide, that charge is always going to be -1. And if we come over here and we apply that rule to the situation, then oxygen will have a -1. Let's see if that fixes things. Well, -1, 2 oxygens, so 2 minus. Well, now things work out here. So that is going to be our reactant side. So again, always just got to double check. If oxygen is in that peroxide, it's going to be -1. On the product side, oxygen, 2 minus. So there's only 1 of them. Total contribution there. Hydrogen, going to be +1. There are 2 of them, so 2 minus, 2 plus. So in this case, same charges. Again, we don't have a peroxide, so we're good there. And the last one, oxygen, normally it'd be -2, but remember our rule that if we have a single type of atom, even if we have diatomic gases, it's going to be 0. So oxygen here has no charge there. So looking at the hydrogen, well, hydrogen has +1, +1, so like nothing's happening to that hydrogen atom. But if we take a look at our other element, oxygen, starts as a -1, but when it breaks down and forms the water molecule, well, this oxygen is 2 minus. And when the other parts of oxygen break down to form that oxygen gas, this oxygen has no charge. So here oxygen is being both oxidized and reduced. So that's one half reaction, and then our other half reaction is going to look like that. So this is our oxidation half, and this is going to be our reduction half. So that's what we call a disproportionate reaction. Anytime you see that the same element is being both oxidized and reduced.